So today we'll look at some transistor parameters and then examples on how to determine the operating region of a BJT. All right, so first up is junction breakdown voltages. Okay, so transistor, a BJT, is made of two back-to-back PN junctions. And so it behaves like any other PN junction diode, whether it's a PNP transistor or a NPN transistor. We are either forward biasing or reverse biasing these junctions. And so like any other PN junction, these junctions also break down. So if you reverse bias any of these junctions, they will break down similar to a PN junction diode. Okay. And we saw this in the lab where we can use this property, well, not property, but this characteristic to determine which terminal is the emitter and which is the collector. So if you reverse bias any of these PN junctions, they will break down like any other PN junction diode. But the difference here is that the BJT is not a symmetrical device. The collector is the least doped out of the three terminals, or the three structures, and the emitter is the most heavily doped. And because it is the most heavily doped, the base emitter junction breaks down at lower voltages. So it have a characteristic similar to a Zener diode. And so this breakdown voltage would be around less than 10, typically. And we saw this in the lab too when we did experiments with the 2222 transistor. The breakdown voltage was around 9 volts. And so this would be for the emitter base junction or the base emitter junction, right? Because it's very heavily doped. For a collector junction, breakdown will occur, but, and I'm going to exaggerate this slope right here, breakdown will occur, but this breakdown will be far larger than 10, probably close to the hundreds. Hundreds of volts. Let's just stick with this. Some base collector. And obviously in the lab, we didn't go that far, right? You went to 60? Oh, 16, yeah. You went to 16. But after we are done next week with the CE amplifier, if students wish, you can apply reverse voltage exceeding, well, we can go max of up to 30 volts in there. But I don't think it's still gonna break down. Okay, so that's the junction breakdown voltages. For the most part, when you reverse bias these junctions, the current is due to the minority charge carriers crossing over the junction. And so it's just reverse saturation current IS, which would be in femtoamps, 10⁻⁻15, 10⁻⁻16. Too small to be measured with the instruments we have in our labs, right? Okay, so that is the junction breakdown voltages. Then let's talk about the base transit time. The base transit time is the time it takes for a charge carrier emitted by the emitter to cross over to the collector side. So again, whether it's PNP or NPN transistor, base is in the middle. We have emitter on one side, we have collector on the other side. We forward bias the emitter base junction. The emitter emits charge carriers that cross into the base and then are injected into the collector side. So the time it takes for it to go from the emitter to the base to the collector side is known as the base transit time. And that is given by, if I can find my notes. Yeah. Tau F. Okay, tau F. And tau F is given by WB square divided by VT 2VT times mu n. Okay. However, is the forward transit time or the base transit time given by WB square or 2VT times mu n. So let's break it down. WB is the width of the base, right? WB is the width of the base, which makes logical sense. Obviously, it's a physical crossing over, so base width. VT is the thermal voltage. And you can see mu n is the carrier mobility. In this case, it's the n carriers, meaning the electron mobility. If this was a PNP transistor, the mu n would be replaced with mu p. So this is for a NPN transistor. For a PNP transistor, same equation. Again, hole mobility, right? Okay. So why is this parameter quantity important? Well, if you think back to chapters 1 and 2, yeah. So if you think back to chapters 1 and 2, where we talked about holes and electrons, charge carriers moving in the crystal lattice. Electrons have higher mobility than holes. Mu n is more than twice as mu p. Okay, so mu n is higher than mu p. That means if you make a device where the electrons are the primary charge carriers, they would work faster than a device that has holes as the charge carriers. NPN transistors, it's electrons, charge carriers. PNP transistors, it's holes as the charge carriers. So NPN transistors, hence, are faster than PNP transistor for the same physical construction. Okay. And that's one of the reasons why they have been historically preferred over PNP devices. Now, there are other, improvements that have been made over the years, so they can make changes in the design and have PNP transistors also work at the same speed as NPN. But again, if you're talking about the exact same design with the exact same materials, then direct comparison, NPN will always be faster than PNP. That's one important consideration. A second one is that it takes time for a charge carrier to transit, meaning it's moving from point A to point B. If you apply an AC signal that is alternating, then a charge carrier could move from point A to point B and it would reverse direction from point B to point A. So if you apply a signal, an AC signal that has a time period, meaning a very high frequency AC signal that has a time period that is smaller than the transit time, the transistor would not be able to operate correctly because the incoming frequency is higher than the speed of the charge carrier. And that is given by, well, actually that places an upper limit on the operation frequency, and that can be given by this equation. One over 2 pi tau f. Similar to, yes, question? No, it says base transit time, but remember, it's going from the emitter all the way to the collector. It's transiting the base. So it's It's originating in the emitter, goes into the emitter, goes into the base because it's forward bias. But then the base is so small, the charge carriers do not have enough. If it's NPN transistor, electrons are emitted from the emitter. There aren't enough holes in the base to recombine with the electrons. And because it's so thin and there's a positive charge at the other end, they're injected or pushed into the collector or attracted by the positive charge. Yes. It's just frequency, yes. There is a small derivation. It's there in the book. I can show it to you outside of class. Excuse me. But again, two major considerations. One is the speed of NPN versus PNP BJTs, and the other one is the upper limit of the operating frequency. Okay. Then there is diffusion capacitance. Well, diffusion capacitance arises because there is charge stored in the base. When you apply base emitter voltage, charge carriers are coming in, it builds up charge in the base before the current can actually change. Okay. And so because of the change in charge, because of the applied voltage, dq or dt, we have capacitance that swarms in the base region, specifically between the base and the emitter. That is known as the diffusion capacitance. So diffusion capacitance arises because of the applied voltage and the charge stored in the base region. Okay. And typically it is modeled as a capacitor between the base and emitter, attached in parallel to the base emitter terminals. So diffusion capacitance is given by CD is equal to IC, the collector current, or VT, what's the transit time. Okay, it's C825. Then we have something known as the beta cutoff frequency. Okay, the beta cutoff frequency displays the relationship that beta has with the frequency. So far we have talked about beta as the current gain, and we say it's a constant, right? But nothing's ever truly a constant. It either is affected by temperature, or in this case, it's affected by the frequency. And the reason it's affected by the frequency is let's draw out this equation. Okay. So beta cutoff frequency. As the frequency increases, the current gain is going to start decreasing. So at lower frequencies, and by lower, I mean less than kilohertz, megahertz, the beta is almost constant. But as you go higher in frequencies, like hundreds of megahertz, there is a slope that occurs. So if I were to plot beta as a function of frequency, it would start dropping around here. Okay, this would more likely than not be greater than or equal to 100 megahertz or so. High frequencies, okay, high frequencies. And so it begins to cut off. Well, we can define mathematically and derive an expression for beta as a function of frequency. So beta as a function of frequency can be given by beta in the forward region. So beta f divided by 1 plus f over fb square. If you remember from the Bode plots for a high pass and low pass filters. Sorry, it's not FB, it's F beta. And F beta itself is FT over beta F. And FT is the unity gain frequency. Essentially, at one point in this graph right here, somewhere, there will be a frequency where the gain beta is equal to 1. So somewhere along the x-axis, way in the hundreds of thousands of megahertz, there will be a frequency where the current gain of a BJT goes down to unity 1. It's known as the unity gain frequency, FT. And FT over beta F, forward gain, gives you F of beta, and that goes into the equation. And so it places an upper limit. Again, this quantifies the upper limit on the operation of BJTs. So high frequency operation is a whole different area of study. Right, 8:30. I want to get into, let's see. The early effect and the early voltage are named after James Early, so a scientist and researcher working for Bell Labs. And while working with BJT output characteristic curves, he noticed that the slope of the collector characteristics can be extrapolated towards the negative side. And they all seem to intersect in this one single area, kind of around in that region. And that voltage, that value of VCE, came to be named after him. Okay, so if you all recall, the lab characteristics for the common emitter mode, the collector characteristics, you had a very flat line at the lower input currents, you had a nearly horizontal and flat lines. And as the current increased, as the input current increased, the output current also increased. When the output current increased, you may have noticed a slope that occurred in your output characteristics. And we didn't go much beyond, I believe, 10 or 12 volts. But if you go beyond 16, 17, 18, 19, 20, the slope would be even more pronounced. And this, of course, is exaggerated. This slope right here and this value that is shown right here is exaggerated. Usually it's, again, hundreds of volts. It's not like in the tens. Right? Okay. Some students had BJTs, I noticed, where the slope wasn't as much. So if we extrapolated that to the negative side, it would probably be hundreds of volts. But anyway, the more important thing is about the slope that it indicates rather than the actual voltage. Okay. So this is a result of the change in the width of the base region. So this early effect occurs because of the change in the width of the base region. Now, why does this happen? Well, we have a reverse bias junction. And when you have a reverse bias junction, what happens? The depletion region specifically. Well, depletion region is still there, but it expands, right? And since the depletion region expands, the other reason would shrink. Not physically, well, I was going to say not physically, meaning it's not, the dimensions are not changing externally, but inside the region is expanding. And so technically we can say that the base region is actually shrinking. So what happens is here, the emitter base junction has forward bias. And even if it was reverse bias, it is heavily doped. So the depletion region doesn't expand as much as compared to the collector. So when we reverse bias the base collector junction, the collector is very lightly doped. So the depletion region starts expanding. This is the original width in the center, shown by the slanted lines. Okay. And this is a result of reverse bias. And when that happens, the base width has shrunk from WB to WB prime or WB dash. Okay. So now your base region has shrunk. Currents are coming, electrons and charge carriers are coming through. You have a shorter base, smaller base region to actually transit through. And so transit time is less. You have higher collector current flowing through. And because you have higher collector current flowing through at higher voltages, you see a higher slope. So it's a result of higher current because of smaller base. Okay. So the base shrinks because you're increasing the reverse bias on the collector side. And because the base is shrinking, the collector current increases. Because the collector current increases, we have now a slope. If it didn't increase, it would be almost constant, like an FET characteristic. That makes sense, right? In this case, it is increasing, so we have a slope. And that decreases or actually increases the output resistance of the BJT. Okay. And so that is another parameter that we have to consider when we are designing a circuit using BJTs. All right, we haven't taken a pause, so let's take a pause. Let me know if you have any questions. Now we'll get into the fun stuff. Where do you want to be right now? Okay, so let's get into some examples, okay? So when we are designing or analyzing a circuit, we want to determine what operating region the excuse me, the transistor is operating, the circuit is operating in. So we already know this, but I created this slide so that it's far more visible in terms of the voltages. So if emitter and collector junctions are both reverse bias, then the transistor is cut off. If they are both forward bias, the transistor is in saturation. If the emitter junction is forward bias and collector junction is reverse bias, then it is in the forward active region. Okay, but what does it mean in terms of the voltages? Well, this is the collector, emitter, and the base. And it's an NPN transistor. So it's an NPN Actually, let me place it right here. N, P, N. So the collector voltage is higher than the base, and it's reverse bias, PN junction. And the emitter voltage must be higher than the base. Here, N, P, N. Both junctions are now forward bias. Collector, base, emitter. And so base voltage must be higher than both the collector and the emitter. And then, of course, in the last one, and collector, base, emitter. So we'll keep this in mind as we go along solving example problems. All right, so we are given this transistor circuit, a resistor at each of the terminals, RB, RC, and RE, and we are asked to determine the operating mode. Okay, values for all the resistors are given. Value for VBB is given. VCC is also given. And then we can determine all other values from the resistors and the voltages. So V1, V2, and V3 are given to us. All we need to do is to determine which of the voltages or which of the terminals is higher than the other. And we can determine either forward bias or reverse bias, and then determine the operating region. Okay. Okay. So what do we think? V1 is 2 volts. So base is at 2 volts. V2 is 1.3. That's an indication right there. And VC is 4 volts. So we write down 4 volts there. So first step is always to check the base emitter junction. Base emitter junction. Because you only have one option. Okay. If it is reverse bias, then it's in cutoff. We don't need to do anything else. We don't need to check the other junction. Even if the other junction is forward bias, then it's in reverse active, it's still not going to turn on. Basically, it's cut off. Okay, so the first junction you always check is the base emitter junction. If it is reverse bias, meaning the voltage is larger than 0.7 volts, then it's in cutoff. Now, if it's in forward bias, then you have two options, either saturation or active. Then we perform further few more calculations and determine which is which. So here, VBE is VB minus VE. So on or off? VBE is 0.7 volts, which is basically the forward bias diode voltage drop. So if VBE is 0.7, that means it's forward bias. So base emitter junction is forward bias. So not in cutoff. Okay, not in cutoff. So now we have two options, active and saturation, and we'll test both. So let's calculate VBC. And VB minus VC is what? minus 2 volts. Minus 2 volts. So it's minus 2 volts. That means the junction is reverse bias. If it's reverse bias, that means it is active. Active mode. Check VBE. VBE is 0.7. If it's 0.7, that indicates it's forward bias because that's the diode, forward diode voltage drop. If it's larger than let's say 0.7, 0.8 volts, that means it's reverse bias. So we checked for active mode because it's reverse bias. Let's check saturation. If the transistor is saturated, then VCE would be less than 0.4 volts, typically around 0.2 or less. Okay. So to test saturation, VCE would be less than or equal to 0.4 volts. And I said typically around 0.2 or less. So what is VCE for us? In this case, VC minus VE, and that is 4 minus 1.3, 2.7 volts. So it's VCE is larger than 0.4, hence not saturation. So even if we were to make an assumption, either with saturation, we would still obtain the exact same answer. Okay. Does that make sense? Good. All right, let's take a 10-second pause for quick questions. Okay, we have time for the next example. Any questions? No? All right, let's look at example 2. So we are given again a NPN transistor. We are provided with the values, and we are asked to determine the operating mode. Now, in the previous example, the voltages were directly given to us, just just to get students started. Now we have to calculate these voltages by applying some equations. Okay. So beta F is given to us. We are asked to determine all BJT voltages and currents. Well, BJT voltages and currents meaning VB, VC, VE, IB, IC, and IE. Okay. So we can begin by inspection. Okay. The first thing I notice is that the base is connected to ground. That means VB is 0 volts. I don't know the voltage of the emitter, but I can see the emitter is connected to a negative -5 volt supply through the RE resistor. Okay. To the RE resistor. And so my inclination is to assume that the base emitter junction is forward bias. And if it's forward bias, then VBE is 0.7 volts. We are assuming, but we'll just assume the standard 0.7 volts. So assume 0.7 volts. And if that is 0.7 volts, then I can find IE. All right, so if we assume VB is 0.7, then VE is VB minus VBE. Right. Now we can apply Ohm's law to RE and determine IE. So IE (4300). That comes to be, well, 1 milliamp. Right? 4.3 divided by 4300. 1 milliamp. And now that we have IE, we can calculate the other two currents also. Right? Beta is given to us. Beta, we can find alpha. From alpha, we can find IC. And from IC, we can find IB. Okay. So alpha is beta over beta plus 1. So it'd be 125 divided by 125 plus 1. That gives me, actually, I don't have this. What does it give me? Calculate someone. 125 or 126. 0.99 something. Thank you. 0.99206. Yeah, the same thing. I just wanted to show logical sequence. And then IC over IE, of course, is alpha. So alpha times IE gives me 0.992 milliamps or 0.99206 milliamps. So far, so good. All right. So now we have IC. We can find VC from there, apply the same thing, but at the collector terminal. So IC can be defined as VCC, or 5 volts, minus VC divided by 2000, which is RC. Actually, RC. VC is ICRC VC or RC. Pi minus ICRC. Well, I'm going wrong. Hold on. So IC is 0.992 times 10 raised to minus 3. Times 2000. VC. And then once we solve this, we should obtain VC as approximately 3. No, it's 2000 times this, so that goes away. So 2 into 1.8, 1.8 minus, we get minus 3, yeah. So yeah, that's what tripped me up when I was rearranging the terms. I was like, how am I getting a negative value? Once I put in the numbers. Okay, so we have, what do we have? We have VE, we have IE, we have IC, we have VC. And we also have VB already. And I guess that's it. So now we are ready to determine which junctions are forward bias and which are reverse bias. Right? We need 3 voltages to determine the region of operation. So what do we see? We already knew that the base emitter is forward bias, so it's not cut off. If it's not cut off, it's either active or it's in saturation. Right? It's either inactive or in saturation. So which one do you want to choose? Well, there's a process that I was going through, but yes, that is correct. Yes. So if we see VBC, VB minus VC, 0 minus 3, that gives us a negative value. And because it's negative, that means the collector base junction is reverse bias. And hence active mode. If we tried saturation, we need to see if VCE is less than 0.4, which in this case, VC minus VE, 3 minus of minus 0.7, which would be 3.7 volts, larger than 0.4, hence not in saturation. It's again in active mode. All right, does the process make sense? The reason I'm asking is because I'm going to do student practice with a different value of the resistor. Student practice. No, just whenever. Outside of class. Outside of class time. So I think everything's the same, except change RC to 10, 12. Let's see if we make it larger, voltage drop. Let's make it 15K. And then determine the region of operation. And that should push the transistor into. What do you think? If we change RC, that's, well, that's it's an educated guess, but how about a calculated guess? But anyway, that's is something else want students to practice. If you want to practice now, that's okay. It doesn't take too long. But I also want to talk about a couple of biasing circuits. So let's see, we have a couple of minutes left. All right, so we talked about bias and why it's important, right? We want to apply external energy or external sources to our BJT device, force it or to constrain it to work at a certain point, right? If we wish to use the BJT as an amplifier, then we want the operating point to be somewhere in the active region, right? And so there are several biasing methods. Three of the most common ones are showed here. First one is a fixed bias. Fixed bias has a base resistor and a collector resistor connected directly to the voltage source. That single voltage source applies a voltage or supplies a voltage to the base as well as the collector. This terminal on the left is V in. This is V out, meaning that's where we would take, we would send the AC input and collect the AC output. And then we have the emitter bias, where the emitter is not connected to ground, but there is a resistor connected to it. Now, there are analyses that we perform on here. Typically, we perform the analysis by applying KVL or KCL on the input and the output side. So we'd apply KVL or KCL to generate equations. Okay, and you apply it to both. Input side and output side. Okay. And then there's load line analysis also that we perform, but we're not going to go too deep into that. The drawbacks of both fixed bias and emitter bias is that the output current is highly dependent on beta, or the Q point becomes dependent on the beta. Okay. And if it's dependent on beta, that means your biasing circuit or your values of the resistors and the voltages that you use would work for one BJT, but could not work for another one. So we want a circuit or design a circuit that is independent of beta, and that's where the voltage divider bias comes in. The voltage divider bias is so-called because we have a voltage divider network on the input side, and you can easily design a BJT circuit to work as an amplifier by using a single supply. A single supply, you don't need to use dual power supplies. Okay, and then that is something we'll look at on Monday. So I want to, on Monday, we'll have a quiz, and then followed by the load line analysis of voltage divider bias in preparation for the lab. So we'll skip ahead a little bit, and then we'll look at a few other circuits. Okay, so we'll end class here today, and I will see you all on Monday. Again, there is a reading assignment. There will also be another homework assignment, and then we will have a quiz on Monday, based only on the BJTs. Okay, only on the BJT.